I hope you've had a chance to look over the warm-up problems. Let's see if we can come up with some main foundations of probability through answering these questions. If the probability that it rains today is 20%, then what's the probability that it does not rain? 80%. Writing both probabilities as decimals, 20% would be 0.2 and 80% would be 0.8. So when we're looking at 20%, here's just a quick refresher for you about percents. Percent means per 100. So we would write this as 20 divided by 100. Anytime you see a percentage sign, to get that number into its decimal equivalent, we would divide by 100. So dividing by 100, we can cancel those zeros. 2 divided by 10 would be 0.2. For a fair coin flip, probability of heads we already saw was 1/2, probability of tails is 1/2, or if you put 50% for those, that's totally fine. Writing them as decimals, 0.5, 0.5. We want to fill in the missing probability for partly cloudy, and then complete the table on the probabilities in percents. How would we figure out what the probability of partly cloudy is? We are making some assumptions that these are the only possible outcomes for the day. It either rains, it's overcast, it's partly cloudy, or it's sunny. And we have some probabilities filled in. How do we determine the probability of partly cloudy? Well, you might have gathered from some of these problems up here, if I add 0.2 and 0.8, what do I get? Or if I add 0.5 and 0.5, what do I get? I actually get the same number. The same thing's going to happen down here. If I add all of these decimal numbers together, plus my unknown, I should end up with that same answer. Yeah, it's 1. So what number added to 0.15, 0.30, and 0.10 would give me 1.45? Changing into percents, since all of these are 2 decimal places, if we're wanting to go back into percents from decimals, we multiply by 100. 100% is equivalent to 1. We're multiplying by a special form of 1 when we do this. And multiplying by a special form of 1 does not change the actual number, it just changes the look of the number. It makes the number equivalent but in a different form. And so multiplying these by 100%, 0.30 becomes 30%, 0.45 becomes 45%, and 0.10 would become 10%. This first foundation of probability, can you determine what it is? Using the word sum, meaning adding together or total. Hopefully you came up with something along the lines of all probabilities for a sample space sum to 1, or 100%. If something is absolutely certain to happen, there's no doubt at all that it will happen, then the probability is 100%, or 1. This is the maximum probability of an event occurring. We cannot have a probability bigger than 1. If something is absolutely impossible to happen, it is never going to happen, then the probability is 0. If something is impossible to happen, then this is the smallest probability we can have. Negative probabilities do not exist. They don't make sense to have a negative number for a probability. So, the second foundation of probability defines the range of possible values. We just found that an impossible event has a probability of 0, and a certain event has a probability of 1. And that means for every single event we could possibly have, every single event, the probability of that event must be between 0 and 1, inclusive, meaning it could be 0 and it could be 1, but it has to be between those two. We can never have negative numbers, and we can never have probabilities bigger than 1. So if you ever make a calculation for probability and you get a probability bigger than 1, something's not right. Or if you get a negative number, again, something's not right. We have to have our probabilities between 0 and 1. Backing up for just a moment, up here with this first foundation of probability, we can write this in some fancy symbols. So I'm going to try to introduce those fancy symbols to you. If E is any event in the sample space, then the probability of E added all together equals 1. This symbol right here that looks like a sideways M, this is a Greek capital sigma, and in mathematics, that symbol means sum. Add them all up. And so if you see that symbol, which we will throughout this course, we'll see that sigma. It just means we're going to add everything up. So that's the first foundation of probability. The sum of all probabilities equals 1 in a sample space. And the second foundation of probability, all probabilities must lie between 0 and 1. Now let's take a moment and break down this word sample space. If we're determining the sample space for each of these events, we want to write down all of the possible outcomes. Tossing a coin, we've done. We could have a head, or we could have a tail. Oftentimes this is abbreviated as H and T, but this is our sample space. Rolling a 6-sided die, we saw this one earlier too. The numbers 1 through 6. Answering a true-false question, well, it's either true or it's false. So we have 2 outcomes there. One more example for a sample space. Remember that sample spaces are outcomes. What can we get? So here we have the situation of choosing a marble from a glass jar that contains 1 red marble, 3 green marbles, 2 blue marbles, and 4 yellow marbles. What outcomes do we have? There are 4 outcomes in this sample space. We could draw a red marble, a green marble, a blue marble, or a yellow marble. Those numbers in this scenario would help us find the probability of these outcomes. So an example, probability of drawing a green marble, because I have 3 greens out of 10 total marbles, 1 plus 3 plus 2 plus 4, then I would get 3/10 or 0.3 as the probability of drawing a green. So that is a different question that's being asked. But I want to make sure that you have a comparison between the two. So the sample space is listing out the outcomes. What outcomes do you have? And the probability is the actual numerical calculation of getting that outcome, getting one of those outcomes in the sample space. All right. The last thing I want to talk about in this part of our lesson is rounding rules. When it comes to probabilities, I differ a little bit on the textbook because I think probabilities should either be a reduced fraction, meaning our denominators are between 2 and 10, denominators being the bottom number of the fraction, or rounded to 3 decimal places. If you're getting a decimal answer for a probability, you should have 3 decimal places there. But if the probability of an event is very small, we round it to the first non-zero digit after the decimal. So here we have this number 4.699 times 10 to the negative 5. This is what we call scientific notation, with that times 10 to the negative 5. Here's our decimal notation written out, and we go all the way to the first non-zero number, that's a 4. but we need to round it appropriately. If you need a refresher on rounding, I will include that after this lesson as an optional viewing. But we would round by looking at the very next number to the number we want to round to. We want to round the 4. So we look at the next number, 6. 4 6 is closer to 5 than it is to the 4. So this 6 here means that we're closer on the number line to the 5. So that's why we round it up to 5. When you're in your calculator working with these numbers and you get a very small number like this, your calculator does not display it in scientific notation. It actually displays this number like this, 4.699 e negative 5. So this e minus 5 part corresponds to the 10 to the negative 5 in the scientific notation. Just be aware of that if you see that on your calculator when you get a really, really small number. The e means exponent of 10, and that exponent would be negative 5. Any troubles with that, feel free to reach out. And in the next part of our lesson, we're going to talk about tree diagrams to help us count sample spaces.